Hello and welcome everyone. This is Professor Rajesh Varapte, a book author of 25 plus engineering books. Dear students, today's topic is Maxwell's equation. What I observed, there are different sets of Maxwell's equations. So in the exam, students are finding it difficult to generate every new set of Maxwell's equations. So in the today's session, I will be teaching you some basic tricks. If you remember only one set, you can generate the remaining set by using the tricks. So before studying the Maxwell's equation, let us recall few things. In earlier topics, we have discussed E bar is electric field intensity, H bar is magnetic field intensity, D bar is electric flux density, B bar is magnetic flux density, J or J bar, it is a vector, so it is current density, and we know that it is a current density, so it is current upon area. Next notation is rho v, that is volume charge density. One more point, in maths or in any other subject, you might have come across this notation. This is called as a delta. This is the fourth letter in Greek alphabet. Related to delta, we'll be using this notation, which is called as a del, or sometimes it is called as a nabla. It is a vector operator which is related to partial derivative. The question arises, am I using Maxwell's equation in my real-time life? Yes, definitely. If you come across electricity or a very common example, every one of us make use of cell phones. So there we are using Maxwell's equation. What are these Maxwell's equations? Basically, Maxwell's equations indicates the interference of electric and magnetic fields. Now there are different sets of Maxwell's equation. Every set contains two parts. One is called as a point form or differential form. Another is called as an integral form. Now, to start with, I am considering a set of Maxwell's equation for time varying fields. As the name indicates, the quantities are varying, changing with respect to time. So it is called as a time varying field. First is the point form or differential form. These are the four equations. This order of Maxwell's equation is very important. First equation is del cross E bar is minus da by B bar by da by T. Now before proceeding, one more important point that everyone should know. There are three important operations we will be using throughout the subject electromagnetics. One is, if I will write del into any scalar, for example, if I will consider a voltage is a scalar. So if I will write del into V is voltage, which is a scalar. So del into V, this operation is called as gradient operation. Next is del dot of any vector. For example, if I will write del dot D bar, just now I explained you D bar is electric flux density. This operation del dot of any vector, as an example I am considering D bar, is called as divergence. And next operation is del cross of anything. Del cross of say E bar. E bar is electric field intensity. It can be any vector. So if you come across del cross of any vector, it is called as curl. So three important operations you need to remember. Del into any scalar is gradient. Del dot of any vector is divergence. Del cross of any vector is called as a curl operation. Now coming back to this set, we are talking about set of Maxwell's equations for time varying fields. These are the four Maxwell's equations for time varying fields. We have already discussed the meaning of each notations. And second is the set of Maxwell's equation which is in the integral form. As you can well observe, almost every equation contains the integration sign. Another important concept. In this subject, when we write this equation, you might have come across this notation. It is called as closed loop integration. The question arises, why I am using closed loop integration? Why not normal integration, like only integration sign? Why not this sign? I'm using this sign which is called as a closed loop integration. This is because You have studied Gauss law. Gauss law is applicable if and only if the surface is closed. If there are openings in the surface, Gauss law is not applicable. So throughout the Maxwell's equation, whatever integration we are performing, that is closed loop integration. Now, these are the four equations which are in the point form. Remaining is the set of Maxwell's equations which are in the integral form. We have already discussed the meaning of each notation. As I said, you just have to memorize one set, that is the set of time varying fields, 4 Maxwell's equation in the point form and 4 in the integral form. All the remaining sets can be well generated if you know this set. As I said, if we know this set, we can generate the remaining sets. So let us first generate the next set, that is Maxwell's equation for free space. As far as the numericals are concerned, mainly numericals are based on this set, that is the set of Maxwell's equation for free space. Now remember the basic thing. If you know the Maxwell's equation for time varying fields, then to generate the Maxwell's equation for free space, remember the condition J bar, that is current density, must be 0, and rho v, that is volume charge density, must be 0. Also keep in mind J bar is current density, so J or J bar is given as current upon area. So if I am saying J bar is 0, that means naturally current is also 0. And one more thing for your information, when we write notation I in this subject, by default it is IC. IC is conduction current. There is one more current which is called as ID, where ID is displacement current. Alright, so to generate the next set of equations, you just need to remember these two conditions. J bar is 0 and rho v is 0. For example, now if I know this set of time varying fields and now I want to generate the Maxwell set for free space, then keeping in mind these two conditions, J bar 0 and rho v 0, in first equation there is no J bar and no rho v, so first equation remains as it is. In the second equation, J bar is 0, that means I will have to remove this. Third equation, look at the condition, rho v is 0, so I will have to make it 0. These are the four equations for free space in the point form. Similarly, in the integral form, in the first equation there is no J bar or rho v, first equation remains as it is. Second equation, there is no J bar and rho v, but there is a term of I. As we discussed, if J is 0, I becomes by default 0, so this term will get vanished. In the third equation, we have rho v, look at the condition, rho v is 0, that means this RHS part becomes 0. So this is the set of Maxwell's equation for the free space. As I said, maximum numericals are based on this set, that is the set of Maxwell's equation for the free space. The next part is the set of Maxwell's equations for good conductors. Like the previous set, remember the conditions. For good conductors, first condition is J bar, that is current density, is very greater than da bar d bar by da bar t. D bar is electric flux density. Second condition, rho v, that is volume charge density, is equals to 0. Now, keeping in mind these two conditions, I am considering this original set of Maxwell's equations for time varying fields, and I have to generate the Maxwell's equations for good conductors. Look at the first equation. First equation remains unchanged because there is no J term or da bar d bar by da bar t term. In second equation, we have this J at the RHS J bar plus da bar d bar by da bar t. Look at the condition. J bar is very greater than da bar d bar by da bar t. That means I can well cancel out the second term and only J bar is left at the RHS. Third equation, del dot d bar is rho v. This is the original equation, but condition is rho v is equals to 0. So third equation becomes del dot d bar is equals to 0. These are the four equations in the point form or differential form for good conductors. Look at the equations and integral form. First equation remains as it is because there is no J bar and da bar d bar by da bar t term. In the second equation, I have da bar d bar by da bar t and current I. Do remember, current I is related to current density as J or J bar is current upon surface area. Surface area is, yes, I will repeat, J, that is current density, is I, current upon surface area. So this I is indirectly related to current density, and condition is current density is very greater than dA by d bar by dA by t. That means I will have to delete this second term, so only current is left. Now a common mistake. See, we are writing equations in integral form. So at the RHS, only current is written. It is not sufficient. I need to express current in terms of integration as it is integral form. How to do it? I will tell you simple trick. Refer the basic equation. Current density J is equals to current upon surface area. So if I want to write equation of current, I can well write this as I is equals to J into S. Now, in electromagnetics, initially always consider the small terms. If I will consider the small terms, then this becomes J bar dot ds bar, because these are two vectors, so I need to put a dot sign. Normal multiplication is not allowed. So once again listen. First write the basic equation. J is I upon S. Consider the quantities are small, then make it more simple. For small quantity I can write di upon ds. It is a vector, so I will write ds bar. So from this equation I can write di is equals to J bar dot ds bar. I have transferred this term to the LHS. Now from this you can generate equation of I, that is closed surface integration of J bar dot ds bar. So a simple technique, if you know the basic equation, express the equation in terms of small quantity, like current is expressed as di, S surface area is expressed as ds bar, then rearrange the equation and finally obtain the equation in integral form. Why I did it? Because I need to generate the set of Maxwell's equation in integral form. Then this is the third equation. Refer the condition. In third equation again I need to put rho v is equals to 0. So this RHS term becomes 0, and this current I need to express it as closed surface integration of J bar dot ds bar. That's what we discussed right now. In the third equation rho v becomes 0, whereas fourth equation remains as it is because there is no J bar and dA by d bar by dA by t term. Now the last set of Maxwell's equation is Maxwell's equations for harmonically varying fields. For this set, do remember some basic things. Replace dA by dA by t by J omega. Omega is angular frequency. Then in place of d bar is electric flux density, use the value epsilon E bar. And in case of B bar, use the value mu H bar. Epsilon is permittivity, mu is permeability. Now we are again referring the same set, that is the set of time varying fields. Look at first equation. I need to modify this equation to generate the set for harmonically varying fields. So here dA by dA by t is there. I will replace it by J omega. Then B bar is there. B bar is replaced by mu H bar. So this equation can be written as del cross E bar is equals to minus J omega. What I did, in place of dA by dA by t, this I have put J omega, and in place of B bar I have to make use of mu H bar, so it becomes minus J omega mu H bar. So simply I can write this value at the RHS as this minus sign remains as it is, so it becomes J omega mu H bar. This is the set of Maxwell's equation, which is the first equation in the point form. Now second equation. Del cross H bar is J bar plus dA by d bar by dA by t. First think about the first term. What I said earlier, if you are getting two equations at the RHS, then you need to club it into one. So how to do it? We know a well-known relation. J bar is called as current density. Do remember this formula? We have already discussed. J bar is expressed as sigma E bar. J bar is current density, sigma is called as conductivity, and E bar we know it is electric field intensity. So for the first term, I am talking about equation 2. For the first term, in place of G bar at the RHS, I will be putting sigma E bar. Then dA by dA by t will be replaced by, so I will write this equation over here. dA by dA by t. I am talking about second term. It can be represented as J omega. What I did, in place of dA by dA by t, I put J omega. d bar is epsilon e bar, so this becomes epsilon e bar. If you combine these two equations, here we have the term j bar plus da bar d bar by da bar t, so this becomes j bar plus da bar d bar by da bar t can be written as sigma e bar plus j omega epsilon e bar. Very simple technique. Take e bar common, it becomes sigma plus j omega epsilon. How to memorize it from the exam point of view? Very simple. Keep in mind, if you are getting two terms at the RHS, try to combine them into a single term. So, as far as the second equation in the point form is concerned, I will write here E bar in the bracket sigma plus j omega epsilon. This is the second equation in the point form for harmonically varying field. Now, for the third equation, I don't have dabba by dabba t term, and keep in mind here rho v is not 0. So third equation remains as it is. If you want, you can well put d bar is epsilon e bar. So it becomes del dot epsilon e bar is equals to rho v. But you can keep it as it is. Fourth equation again remains as it is. If you want to change it, you can well place in place of b bar, you can put mu h bar. So it becomes del dot mu h bar is equals to 0. But if you keep it as it is, then also it will do. Now, about the integral part. Look at the first equation. As we discussed earlier, in case of integral part, there should be integration sign associated with each term. Now, look at the first term at the RHS. I need to replace dabba by dabba t by j omega, and b bar is mu h bar. So this term, if I am talking about first equation, this term can be written as closed surface integration of, this should be closed surface integration. In place of dabba by dabba t, I am putting j omega, b bar is mu h bar, dot ds bar remains as it is. Now this j omega mu are constant terms, so can be taken outside the integration. So it becomes j omega mu. Inside the integration, you will get h bar dot ds bar. So the first equation can be well written as, LHS remains as it is. This will be minus j omega mu closed surface integration of h bar dot ds bar. So this is the Maxwell's first equation in the integral form. Now second equation. Again, try to recall the things what we learned earlier. If you are getting two terms at the RHS, try to club these two terms in a single term. Now the first term is current I. We have discussed earlier that current I can be expressed as closed surface integration of j bar dot ds bar. So current I is expressed as closed surface integration of j bar dot ds bar. Now, again, I need to club these two terms. So we know the well-known relation. J bar is sigma e bar, so I can put, I'm just talking about the first term, that is term related to I. So I can well write this equation as closed surface integration of sigma e bar dot ds bar. This is the first term. Now I need to add a second term also in this equation. So if I am combining the two terms, I can write it like this, plus, see, this first term is related to current I only, plus second term surface integration remains as it is. In place of dabba by dabba t, I need to write j omega. In place of d bar, I need to write epsilon e bar dot ds bar. Now, in this step also, I will be doing same thing. So closed surface integration of j omega epsilon e bar dot ds bar. Now you can take this integration sign, I will mark it, integration sign, and e bar dot ds bar, these two terms can be taken common. So simply at the RHS, I can write this equation as, keep in mind what we are taking common, integration sign and e bar dot ds bar. So remaining things are sigma, this term, and j omega, and in between there is a plus sign. So at the RHS, I can write this term as sigma plus j omega epsilon and closed surface integration of e bar dot ds bar. This is the Maxwell's second equation in the integral form for harmonically varying fields. Third equation, there is no dabba by dabba t term, so you can keep it as it is. If you want to further simplify it, in place of d bar you can write epsilon e bar, but this is okay. Fourth equation again will remain as it is. Well, you can put b bar is equals to mu h bar and RHS is equals to 0. So this is the set of Maxwell's equations for harmonically varying fields. Dear students, I tried to explain you how to memorize the different sets of Maxwell's equation. In the next video, I will explain you how to solve numericals related to Maxwell's equation. Till then, keep watching such videos and of course keep studying. Thank you. Thanks a lot.